Okay, so we talked a little bit about strong acids, weak acids, dilute concentrations, high concentrations. This time we're going to talk a little bit about something called conjugate acid-base pairs. And these come from the Bronsted-Lowry acid-base theory, which we also talked about in the last class. So here we've got a compound. This is methylamine, CH3NH2, and it behaves as what type of acid or base when dissolved in water? Now here's the problem. All right, we got two theories. Does this fit, just one letter? Does it fit two letters? I want you to think about that. Okay, we actually talked about what these kinds of compounds do. They act as weak bases, or as a base. So what it's going to do is methylamine is going to break water apart so that it's going to end up with an NH3 group with a positive charge and a hydroxyl group. Now, the compound itself, methylamine, does not have an OH in it. So that eliminates Arrhenius base. You can also see that it's not donating hydrogens, it's accepting hydrogens. So it can't be an acid, either an Arrhenius acid or a Bronsted-Lowry acid. So the only choice you have left is a Bronsted-Lowry base, and that's what the correct answer is. Now, conjugate acid-base pairs. They're derived from Bronsted-Lowry acid-base theory. So let me just review that real quickly. In this theory, in the acid-base reaction, a proton is transferred. That's a hydrogen ion. So the acid donates the hydrogen ion in Bronsted-Lowry theory, so you have to look at a reaction to get the answer. The base accepts the hydrogen ion, the proton. So here's an example. So we got HCl, H2O. It looks like the O is picking up a hydrogen, and it looks like the HCl is losing a hydrogen. Okay, so this must be an acid because it's donating. This must be a base as it's accepting. What about these things that are the products? How do we refer to them according to Bronsted-Lowry acid-base theory? Well, one of them is going to be a conjugate base, and the conjugate base is the product over here that would accept a proton in the reverse reaction. So for instance, if we started out with these and went to those as products, which one of these two is accepting a proton? So if you look at it, I just wrote it in the reverse, it's going to be the chloride ion because the chloride ion grabs a hydrogen from H3O+. So this one is our conjugate base. All conjugate means is which one acts on the product side. And since it acts as a base, it's a conjugate base. Conjugate acid is which one of these on the product side acts as an acid in the reverse reaction. So if we take a look for the conjugate acid, we write the reverse reaction, which one of these two is donating a proton, donating a hydrogen? Well, it can't be this one. It doesn't even have a hydrogen. It's the hydronium ion, which is giving a hydrogen to HCl to make to Cl minus to make HCl and water. So acid, base, conjugate acid, conjugate base. Okay, so let's look at something a little more complicated. Here's another reaction. So we got magnesium hydroxide reacting with HCl, forming MgCl2 and water. Okay, got all the states in there. And so the question is, which one of these two acts like an acid? Well, let's see. This is hydrochloric acid. So I think that one's going to be the acid, but how can we really tell? We look at what happens and look over here and see if the H is still associated with the Cl. There is no H associated with the Cl, so this must have donated an H. Where did the H go? If we look at this compound, that H goes to the OH. That makes water. All right, so what we end up with, this is a double displacement reaction, but what we're ending up with is the hydrochloric acid donating a hydrogen ion to the magnesium hydroxide to form water and magnesium chloride. So our base is a magnesium hydroxide, our acid is a hydrochloric acid. Conjugate base is magnesium chloride, conjugate acid is water. Now, how could we tell for sure? Well, think about the reverse reaction. Look at your two products. Which one has a hydrogen? Well, only this one. So you can't be a conjugate acid unless you can donate a proton. So the only one that can do that is water. So that's got to be the conjugate acid. And if you look over here, this MgCl, the Cl picks up AH. So this must be acting like a conjugate base. Now, in Bronsted-Lowry theory, not only do we determine which is the acid, the base, the conjugate base, and the conjugate acid, we link them together. So what we do is we look for ones that have the same. So for the anion, we're looking for this relationship, the hydrochloric acid and magnesium chloride. So you've got your conjugate acid-base pair. The acid is paired with the conjugate base, and the base gets paired with the conjugate acid. Okay, let's try one more. Identify conjugate acid-base pairs. So here's an example. H2SO4 reacting with NH3, and it's making HSO4 1- and NH4 plus. Which one of these donates a hydrogen? Well, did this become H3SO4? No, it lost a hydrogen. So this one must be the acid. This one looks like it gained a hydrogen. Notice we have charges now too on the products because the hydrogen ion has a 1+ charge. So here, when we're actually adding it to NH3, it's going to end up being the ammonium ion. NH3 is ammonia. So this is our base. This is our acid. Now, think about the reverse reaction. Which one of these two donates a hydrogen ion? Well, NH4 plus becomes NH3, so it loses a hydrogen ion. So it's donating to HSO4 1-. So this, in the reverse reaction, must be the conjugate acid. And the HSO4 1- in the reverse reaction must be the conjugate base. So again, we write the titles underneath or above, and then we connect the pairs. The acid will go with the conjugate base. The base will go with the conjugate acid. And you can see that if you look at them carefully, they're only differing by a single proton, by one hydrogen ion. So this one's got 2, this one's got 1. This one's got 3, this one's got 4. So the ones that are paired together, the base and conjugate acid and the acid and conjugate base, only differ by one hydrogen ion. Now, you have a worksheet that you are going to try to work on. I've got it linked up, and it is basically acid-base reactions, and you're trying to figure out what acts as an acid in a base and what acts as a conjugate base in the conjugate acid. So do your best that you can to try to complete that. It's already linked up.